Welcome to my video, Snow to Water Ratio Explained, Measuring Winter Snowfall. In this video, I explore how much liquid water is obtained when freshly fallen snow melts. Using a simple 210 millimeter diameter cylindrical pan, I collected snow during two different snowfall periods on December 1st, 2025. By measuring the depth of the snow before melting and the volume of water afterward, I was able to estimate the snow-to-water ratio. This ratio is an important meteorological indicator, giving insight into snow density and storm characteristics. In the first observation, the snow depth measured 28 millimeters. After melting, the collected water totaled 180 milliliters. When distributed across the known surface area of the pan, this corresponds to a water depth of 5.2 millimeters. Dividing the original snow depth by the resulting water depth gives a snow-to-water ratio of about 5.4 to 1. This suggests fairly dense snow with a relatively high water content compared to more powdery snow. After the snow was collected, I let it melt and measured the volume. By knowing the dimensions of the pan and the amount of water, I was able to more accurately calculate the depth of the water in the pan as opposed to a direct measurement of the water depth. The second observation involved 21 millimeters of snow depth, yielding only 80 milliliters of meltwater. Converted to depth, this gives approximately 2.3 millimeters of water in the pan. This results in a much higher snow-to-water ratio, about 9.1 to 1, indicating lighter, fluffier snow. This is typical of colder conditions or snow formed from smaller, less compact flakes. When I combine the two observations, the average snow-to-water ratio is approximately 7.25 to 1. The difference between the two measurements, from 5.4 to 9.1, provides a simple, real-world measure of variability. A rough, spread-based error estimate of plus or minus 1.85 highlights how much snow density can change even within the same region, or was due to experimental error. This reinforces the idea that snow is not uniform and that simple field measurements can yield significant differences. This time-lapse video illustrates how snow accumulated over approximately 20 minutes. The time-lapse footage helps convey flake size, fall rate, and accumulation conditions that influence snow density. Dry, powdery snow can produce ratios as high as 15 to 1 or more because the flakes contain a large amount of trapped air. Typical mid-range snowfalls produce ratios near 10 to 1, which is often used as an approximate rule of thumb. Wet, heavy snow, common near freezing temperatures, can have ratios as low as 5 to 1 due to higher liquid content within the flakes. These typical values help place my measurements into a broader context. Every measurement method has sources of error, and simple field setups like this are no exception. Snow settling in compaction can reduce apparent snow depth, while melting during handling can reduce water volume. If the pan is not perfectly level, it will affect depth calculations. Wind or drifting snow may cause the pan to collect more or less snow than the surrounding ground. Finally, ruler precision and parallax error can introduce inaccuracies in the snow depth reading. Understanding these factors helps interpret the results more effectively. Meteorological conditions strongly influence snow density and therefore the snow-to-water ratio. Warmer storms, especially when temperatures are close to freezing, tend to produce wetter, heavier snow with lower ratios. Colder storms create lighter, powdery snow containing more airspace, which leads to higher ratios. Relative humidity affects the structure of snowflakes, determining whether they grow into large dendrites or remain small granular particles. Wind can also alter accumulation by compacting snow in some areas while scarring others, producing uneven depths. I hope you learned a little bit about snow measurement, and thanks for watching.